Okay, we're starting. All right. All right, welcome to the review. We do these pretty much every time before an exam, which for you will be, your exams are on Monday. I try to do them like 2 days in advance so that you get have some time to have this digest and also get working homework. And I find that it's best to try to get your major cram done a couple days in advance rather than try to do it the night before where you get things just swimming in your head. It can be difficult. We're doing something different. We're recording these, so people that can attend should be able to see it, or if you want to see any parts of it again, you can do that. How many people have looked at Dr. Young's lectures online? Most people. Okay, so you know the page to go to. These videos should show up. It's just listed at kind of at the bottom under updates. And so we'll get those. If there's somebody that you know that wasn't able to come today and wants to look at those, you should be able to check those out. I'll try to get them loaded, and they should be up sometime tonight, I guess, is usually how long it takes to process. So that's just something new. As far as the format of these reviews, a lot of you are in the Friday section. Those Fridays are kind of free-for-alls where people, ask questions. These reviews is more like a lecture where I take you and try to take you through the ideas. We will do problems, and I've got these problem sets. These are past exam questions of his, so it's good, particularly for you. You haven't had Dr. Young yet, and you want to know, okay, what does he expect? What kind of questions does he give? He tends to be very physics type questions, not so much on the math. For instance, you've got 4 chapters you're dealing with. The first chapter was on, scientific notation and units, and most people don't have trouble with that. And he's not going to ask a question with that in it, but probably he'll tie that in with another question on the exam where he'll maybe have you convert units. So I'm assuming most people can do those, and so I'm not going to dwell on that. Also, chapter 3 is one on vectors, and we'll use vectors, and more so as we get into the course than we do here. Vectors are a very important tool. Dr. Young primarily focuses on the physics, and so he's not going to get really fussy about using vector notation. You will need to be aware of the basics of the idea of vector notation, and it will be tied in with a problem, and we'll look at some of that. But again, don't expect a vector problem. Vectors are a mathematical tool that we're going to use. Oh, one other thing, chapter 1 does a thing with significant figures. A lot of you have taken like chemistry here where they really make a big issue of significant figures because very often you're doing problems that you're making measurements, and it's important that you don't overemphasize something that is really tiny and you can't control it. Dr. Young is not as fussy with that because, like we're talking about a problem like a car is traveling at 10 meters per second. He doesn't want to have to say 10.00001 meters per second. He just wants to be able to just round things off. Again, it's primarily a conceptual class. You will get solutions, and generally the rule of thumb in the book uses like 3 significant figures. And so you round your answers to 3 significant figures. If you put down 4, he's not likely to, knock you off for that. It's a good idea, though, in calculations, when you're trying to find this, particularly when you're doing your homework and you want to piece things together, is to carry extra places in your calculations. Don't keep rounding every step you take, because if you do a multi-step problem, you keep rounding and rounding and rounding, pretty soon it's not even recognizable. So keep extra places and jot them down. He's not going to mark you off for having too many there. Just go ahead and put them in, and then at the very end you could maybe round it to 3 significant figures. So these are just little details, and again, because chemistry makes such an issue of significant figures, a lot of times students get fearful of that. Let me start off with just a basic thing. Now, primarily what you're going to need to focus on for the exam is really Chapter 2 and Chapter 4. And how many people are all done with chapter 4? Okay, I'll spend a lot of time on that stuff today because this is primarily key exam material. This is where it all kind of comes together, and you can see if you know this stuff. Let's start off with, I've got some, everybody get these things, practice problems. I've got some solutions. We'll take a look at these. I'm not going to do all of them, but I will look at some of them. And a lot of these, what I'll do in these reviews is sometimes do a setup where I won't do all the little math. We'll look at try to get the big picture of what's going on. Let's start off with a practice problem. I've got that number 3. And it's a stunt driver. He starts from rest, and it's best to, Dr. Young is really good with partial credit, so don't just panic. Start to put down what you know. He's got a driver that starts from rest from 30 meters from the edge of a cliff, and it's a good idea to just kind of start jotting things down. Think of the problem like a puzzle, and you're going to just lay out the pieces here. He starts from rest, so that's the initial velocity is equal to 0. He's going to take off, he's going to accelerate, and is going to drive off the cliff. And let's see, let me look at the wording. The stunt driver starts from rest 30 meters from the cliff's edge, of a 20-meter high cliff. And the acceleration is defined by, the acceleration is equal to the square root of t. Okay, and he says, how far from the cliff's edge does the car land? Now, the car is going to take off on a projectile, and there's really kind of 2 parts to this problem. And what I want to do is kind of focus on this first part. And actually, I want to get how fast the car is going to drive off the cliff, so then I can turn it into a projectile problem. And I'm actually going to do that part of it later. Right now, I just primarily want to focus on this idea that it's accelerating.
So quick question.
Yeah.
So in the majority of the problems that we've been doing, it's been constant acceleration. So we will have to deal with non-constant acceleration on this.
Yes. In fact, I'm starting with this one for just that reason. I was going to ask for, what do I do? Okay, good. So how about a kinematic equations? Okay, so I think he's prompting you. Exactly right. And that's one reason I wanted to start off with this one, is because he will, I'll guarantee you, of those problems, he's going to give you one that is a non-constant acceleration. And he defines this way. Okay, this is kind of strange. Let me write it as t to the 1/2 power. Is anybody bothered by the units on that? Acceleration should be what, in meters per second squared. And this is the square root of seconds. Okay. Okay, now he will do this. In reality, usually what the book will do, they'll do something. If they come up with something weird like this, they'll say, the acceleration, a little statement, the acceleration will be in meters per second squared as long as your t is in seconds. So in reality, there's really some acceleration is some constant, let's say k, times the square root of t, and the units of this would have to work out so that the square root of seconds works out and gives us meters per second squared. So don't be bothered by that, and he's not again real fussy with this stuff with the units. He'll get kind of sloppy, and it really needs that little disclaimer statement to really do it properly. But we'll just go ahead and play the game. So the acceleration, let me write that as, just for doing the calculus, is equal to a to the 1/2 power. Then we know that the acceleration is equal to dv dt. So the idea is I want to really anti-differentiate or integrate to get the velocity. The velocity will be a to, let's see, I'll add 1 to this to the 3/2 power. And then, yeah, if I take the...
The 1/2 power?
Yeah, yeah. Not an A.
T to the 1/2 power.
Wait a second. Oh, okay.
Yeah, or 2 to the,
Well, I'm just confused that the A equals, so it would be 8.
oh, okay.
T to the 1/2.
I screwed up already. Yeah, it's a good, yeah, watch me. I try to, be thinking what I'm going to say. I'm also trying to write. And when you see I make stupid mistakes, lots of them, this doesn't happen to you, definitely stop me. Okay, yeah, this will be A times T to the 1/2. I copied it down wrong. So now I'm going to take this I'm going to integrate. I'm going to add 1 to this. So this is to the 3/2. I've got to, when I take the derivative, I've got to have a 2/3 here. Hopefully your calculus is good and you understand that. However, when we do kind of this integration, shouldn't I have an integration constant?
Yeah, so the plus the other.
Yeah, let's just say it's some constant, and the meaning of that physically, at time t equal to 0, we put in a 0 here, and v is equal to that constant. So that's why instead of that constant, we're just going to go v sub I. That's the initial velocity. And let's see, that's probably not enough. I should have looked at these more carefully here. I can also, let's do one more. V is equal to dx dt. So if I go ahead and take the derivative again, I can get this is equal to 2/3. This t is now going to become a 5/2. And I've got to kick in another 2/5 to make that work. Plus this v initial times time, plus some constant, and that happens when t is equal to 0. These terms go to 0, and x is equal to that constant, and we'll call that constant x initial. These are from initial conditions. Let me just do a quick look at my notes because I want to not have to do a lot of math here. Should I have this out? Yeah, so, okay, so actually from what's given, I'm going to need to do what with substituting things in? I want to get maybe the time when it's here.
So the delta x.
Okay, so I'll have a delta x, and so I could write that as x is going to be 30 is equal to, let's say, 4/15 t to the 5/2. I want to solve for t. The initial velocity, what was that? That was 0. Oh, that's nice. Plus 0. And then the initial position, what should I do?
0.
Yeah, I guess I've kind of implied that if the end is 30, this was 0. I should have marked that. And so that's true. And so then we can go ahead and solve for the time. And let me just write down what I got, and you can compare your notes. I've got a time of 6.614 seconds. Carry extra place. We want to get the speed that he's going to drive off, the velocity. And so I would want to take this and stick it back up into that equation. And then the velocity is equal to 2/3 of 6.614 seconds to the 3/2 plus the initial velocity, which is 0. And I can get that velocity, I got 11.34 meters per second. And so he drives off the cliff with that speed. I'm going to talk about projectiles a little later, so I want to come back to this. The reason I wanted to use this one is because we have one of these classic non-constant accelerations. And it sounds like a lot of you are pretty well prepped on that and you're aware of that. Maybe do one more along those lines, and that would be I'm thinking on the little these ones that I call extra problems. These are a little tougher problems, so it sounds like you kind of know what to do here. Let's try this. It's number 2 of the extra problems. Excuse me?
I'm asking if anyone else got that for T. Maybe that's a little different.
Oh, a different number?
Yeah.
You got that? I'm not aware of a problem with it. You know, I can make mistakes, but I think you got the same. Okay. Yeah, thank you. Okay. Yeah. Check that. I think that's it. Yeah. So this is number 2, again, of the extras. And this has a little different twist to it. The speed of a bullet as it travels down the barrel of a rifle towards the opening is given by, and he gives you this speed equation. So that's minus 5 times 10 to the 7th t squared plus 3 times 10 to the 5th times t. Okay, and here he has this little disclaimer where v is in meters per second and t is in seconds. So again, so the units work out. He doesn't have to carefully doctor all his units. Okay, now this barrel of the gun, if you think about it, it's a long barrel. In fact, he wants us to find out what the length of the barrel is. He does say that the acceleration, if you imagine like a bullet or something leaving here, there's maybe an explosion with gunpowder. It's propelling it, and then as it shoots it out the other end, that's sort of when the gunpowder and the expanding gases will cut out. And so he's suggesting that the acceleration of the bullet, just as it leaves the barrel, is equal to 0 at the end of the barrel. Okay, and he wants to know actually what the length of the barrel is his question. Okay, he gives us the velocity. Now it is another one of these types of problems where we've got a velocity as a function of time. How about the acceleration? Is that a function? Yeah, let's check it out. I know acceleration should be equal to dv dt. So if I take the derivative of this, that 2 comes down, that's going to become a 10 or a minus 10 times 10 to the 7th times t plus the derivative of that is just 3 times 10 to the 5th. And we want to find, let's say, the time when the acceleration is 0 at the end. That would have taken a certain time that the bullet goes down the barrel, and that should be equal to 0. And we can solve for the time in that one. And let me just grab my notes. Okay, and I've got a time, let's see, I got 3 times 10 to the minus 3 seconds for that to occur. So how long is the barrel? That's maybe where I want to go the other way. I went from velocity to acceleration. I maybe want to get x, and that should be, or actually, let me state it this way. V is equal to dx dt, so I can integrate this to get x. And so I expect that x is going to be equal to minus 5 times 10 to the 7th. T will be, to integrate, will be go to the cubed. I'll have to have a 1/3 here, so it differentiates right. And then I'm going to integrate this plus 3 times 10 to the 5th times, now this is going to become t squared. I'll have to put in a divide by 2. And I could say, well, there's going to be a plus x initial, but we'll just make this end of the barrel x initial is equal to 0, so we don't have that. Then I can take that time and I can substitute it in to this equation, and when I do that, I came up with x is 0.90 meters, or you could say 90 centimeters is the length of the barrel. Okay, so again, the math isn't too difficult, but the strategy of seeing this and realizing he is going to give you a problem like this. So here's a couple of problems like that. Now, you do a lot of problems where the acceleration is constant. So let's take another look at where that comes from. In fact, maybe I'll put it over here. if the acceleration is constant. And we'll have a whole class of problems like this. Particularly now, you're getting into chapter 5 of the homework. There, if you have a constant force, F equals ma, that implies a constant acceleration. We've got a bunch of constant accelerations in the material we have, is something like projectiles, which we'll get into a bit, where we have a constant acceleration due to gravity. So these are, again, are a important class of problems. Now, not doing them just like that. Let's say I do them in the same form. I'm going to say that if the acceleration is constant, I know that acceleration is dv dt. So the idea I want to anti-differentiate or integrate, I can say that the velocity has to be equal to the acceleration, whatever that is, times time. Okay, so when I take the derivative of this, I get just that constant. Also, I should have some constant of integration. When t is equal to 0, that velocity should be that constant. That's that initial velocity. Again, we can go another step here. We can say velocity is dx dt. And I can integrate one more time to get x is going to be, now it's going to be an at squared with a 1/2 plus the initial velocity times time plus, when t is equal to 0, some integration constant, which is going to be the initial position. We've got that. So these are our basic equations we're going to use for constant acceleration. And you really can do virtually all these problems with just this idea. And this is the fundamental idea. However, there's going to be some other equations here that are listed in the book. You also see them used a great deal in homework solutions. And one is to eliminate the time between these two. Let's look at where they come from, and maybe you'll be a little more comfortable with them. Dr. Young doesn't allow you to bring notes, and so there's not a lot you can bring into the exam, and there isn't a lot you need to bring into the exam. These are definitely you want to be ready with. You could say, well, I don't even need that. I just start with constant acceleration. I integrate once, I integrate again. I've got my equations, so if I forget them, I know how to get them. How about if I take this first one and I solve for time? So I'll say that, let me just write the equation here, at plus the initial velocity. Solving for time, I'll go v minus the initial velocity is equal to at, or let me divide by a. So that's t. And let me put that into this other expression. This is x is equal to 1/2 at squared plus the initial velocity times time, plus the initial position, x initial. And let me stick this in for t. Let me bring this over to the other side. X minus x initial is equal to 1/2 a, and for t, let me put in v minus v initial all over a. We're going to have to square that. That's the time. Plus the initial velocity times the time again is v minus v initial all over a. Let's do a little math here. Let's multiply through by 2a. If I multiply both sides by 2a, a lot of ways of doing the math here. Multiplying by 2a, that's going to get rid of this, and I'm going to end up with an a squared. And I'm going to have v minus v initial all over a squared. Plus, this is going to be a 2a times, and I'm going to distribute this through v times v initial minus v initial squared all over a. And my motivation for that is this a squared is going to cancel with this one. This a is going to knock off with this one. And let me just expand this a little more. This is going to be v squared minus 2v times v initial plus v initial squared plus 2 times v initial minus 2v initial squared. Whew. Okay. Okay, this v initial squared is going to cancel with one of those. I've got a minus 2v initial and a plus 2v initial. These two go out. And so I'm left with, on this side, v squared minus v initial squared. Let me just take that over to the other side as plus v initial squared plus what's already over here, 2a times x minus x initial. And I've got another kinematic equation. Okay, this is a little more of a pain to derive. But what it does is, very often you have problems where typically you solve for time in one equation and you stick it into the other equation. This is really where this came from. And usually we'll write it as v squared is equal to the initial velocity squared. Sometimes we'll throw in a final here just to emphasize the difference in these. Plus 2 times a times x minus x initial. And so that's kind of our third equation. And again, you'll see this very often in homework problems. They go right to this rather than play with these two, although they should give you the same results. Another possibility is to take this one and solve for a. The first one is going to be a is equal to v minus v initial all over a. Wait a minute. Excuse me. Solving for a over t. Get that. Okay. And substituting it into this equation, x is equal to 1/2 a times t squared, v minus v initial all over t squared plus, I'm confusing myself, minus v initial times t. I should be plugging it into A. Thank you. Okay, let me from the top again. I'm trying to rush this too much. Taking this first equation, I'm solving for A. So I'm going to take v minus v initial and divide by t. So that's the acceleration. And I want to put this into this equation. So I do want to do that. X is equal to 1/2 a. That's v minus v initial over t. Yeah, I see what, yeah, and times t squared plus v initial. I don't need an expression for that. Plus v initial times t plus x initial. Okay, and here, this is going to knock off with one of these. I'll bring the x initial over to the other side. X minus x initial is equal to, let me distribute this, 1/2 v minus 1/2 v initial. All of that's times t, getting sloppy again, plus v initial times t. I took that over to the other side. So I've got two of these, and did I screw up somewhere else? I'm feeling like I did. It's okay. This was squared. That canceled with one of these. So actually, I'm okay. I've got all of those. I'm going to have, a v. Let me write this. This is going to knock off this minus 1/2, and a plus 1 is a 1/2 v times t. Minus a 1/2 is a plus 1/2 v initial t, and I write that as v plus v initial all over 2 times t is equal to x minus x initial. Okay, that's what I was looking for. Okay, again, not difficult, other than you could see how my difficulties in trying to write that. But these equations are useful. Now this last one that I'm doing, we eliminate a between that. So if you don't know a, this can be a handy equation to use. I think the easiest way to remember this is just call this the average velocity. Average velocity, we add the final and the initial divided by 2. The average velocity times time would be equal to the distance. So I find I don't use this one a lot, but certainly this one gets used a lot, and I would say probably you want to remember that so you don't have to go through the lengthy derivation. It can save you trouble. Very often in numeric problems, it's not a problem to go ahead and solve for one for t and stick it in the other one. So if you're working along those lines, I would say you can likely get to the answer. You might be a few extra steps, but you're on the road, so you'd want to go ahead and do that.
Will he be giving us primarily numeric problems, or will there
Primarily numeric problems. Sometimes he will have problems where they'll have symbols, and you'll want to use the symbols. And in fact, the number of these that I'm going to be doing, I'll use the symbols first and stick in the numbers later. I think it's actually easier to follow conceptually what you're doing. Okay, so I bumbled through that, but essentially those are your basic kinematic equations. Again, you can use these. What you may want to do, he will allow scratch paper. And as you're getting used to this, I would say, stuff these in your memory and get down, and when you start the exam, take that scratch paper, and I would lay out your kinematic equations, and also remind yourself this is if they're constant. Because then when they're staring you in the face and you're trying to do a problem, you can be looking at these and seeing which one is going to fill the bill. And so that I think can be really helpful. Okay. Let's start with a simple kind of acceleration problem with kind of 1D motion. And I'm thinking just number 1 on these practice problems. Start off with a kind of a simple one. We're going to start with a projectile. We're going to fire. It's 1 meter up, and it's going to go up. It's going to stop, and it's going to fall back down. It's going straight up. It's going to fall back along its line. I'm going to just kind of draw it off to the side that it's going to fall back to the ground from here. It's going to be up there some height above the ground. In fact, that's one thing that he's asking. How high is it going to go? Again, you see I start off with kind of pictures with this thing. It's shot off with initial speed of 22 meters per second. Let's see, is there any acceleration in this? No? Yeah, there's G in there, right? Okay, we got to, and I'm just going to call it G, and I've got the vector indicating that's down, right? As far as the vectors, consider that you're going to get a problem. You're going to want to decide how you want to lay out your coordinate system. Typically, this is like the x-axis. This would be like along my ground. I'm going to have a y-axis that may be along the line of motion. Would be my y-axis. You need to decide which is plus and minus, so as you do the math. It's sort of natural to say, well, I'll just call this the plus direction. Very natural for that. Gravity is the acceleration. Notice it's pointing in the negative direction. When I go to do my equations of motion, I want to find out how high this thing is going to go. And what about when it's on its height, the highest point? What's happening there? If you toss something in the air? Yeah, I throw it up, it's going to go up, it's going to just stop for a moment, it's going to start back down. So the velocity is headed that way. The acceleration, we say, is in the negative direction. And so I'm indicating that here. Be careful about sticking in I'll get to that in a moment. So I'm calling up positive. Any vector that points up is going to be positive. Any vector that points down will be negative. So we want to use that in our equations. Done this with the x. Of course, we can do this also in the y. So instead of x's, we'll use y. And I'll use y is equal to y initial plus the acceleration times time. Excuse me. Yeah.
The height above the ground that it's released is listed as 1.5 meters. Is that what?
Oh, yeah, thank you for catching that. I just put in one. Got another one that's 1.5 meters. Yeah, definitely catch that. Okay, thanks. Oh, and yeah, so now when we put in values here, so this is the generic equation. The y is going to be, I want to get the height of this thing. Actually, I want to get, wait a minute, 1/2 AT squared. I'm sorry. I'm having trouble getting going here. I want the velocity equation. I'm gonna come back to the y equation. Velocity in the y is equal to the initial velocity in the y. Now what do I want to do for acceleration? Normally I say a plus at. This is the one I wanted, not y. Okay, this is the velocity. The velocity in the y, what I want it to be is up on top. I want it to be 0. So that's the final velocity. The initial velocity was in the plus direction. That's 22 meters per second. Plus the acceleration, which is a negative 9.8. Or let me do this. I'm going to write it as, no, let's do it. Negative 9.8 meters per second squared times the time. And so I can get the time that it goes up. Let me call that time t1 going up to the top, because we're also going to have a time going down. Let me get that time, and I got confusing myself because I've done this problem several different ways. And yeah, I get a t1 of 22.245 seconds to do that. And now I want to take that, and I want to take that value into the y equation. So this is where I go to the first one, or the second one. So I really got in this one. Now I'm going to do this one. Y is equal to the initial y plus the velocity initial in the y times time plus 1/2 the acceleration in the y times t squared. So let me put that in. The y should be the height of this thing. I'm going above the ground. So that's I'll just call that h. And the initial position is 1.5 meters plus the initial velocity, 22 meters per second, times the time of 2.245 seconds. Then I also have plus 1/2 at. The acceleration is negative, so that's a negative 9.8 divided by 2 is 4.9 times this same time squared. And we can go ahead and solve for h. And I get the h of 26.2 meters, and that would be the height that it gets up there. So there was that part of the question. What is the maximal height above the ground that the ball rises, and how long is the ball in the air? Whoa. Now the ball is taking this long, that's why I call it T1, to get up to the top. If I want to get how long the ball is in the air, we could say, well, up on top the ball is equal to 0 velocity. It's now going to fall in the negative direction. G is in that direction. It accelerates in the negative direction, going faster and faster and faster as it falls. But we can use this y equation going down. So going down, we're going to say y is equal to y initial plus the initial velocity in the y times time plus 1/2 at squared. The y is going to be back on the ground, so I want to start at 0. I want that to end at 0. It starts at this original height. I've got 26.2 meters, and that's up, positive, plus the initial velocity in the y, but that is 0 in this case. The velocity is 0 up at the top, because I'm starting over, plus 1/2 the acceleration, that's going to be a negative 9.8 times time squared. And so here I can solve for t. This 0 here, that term goes away. I'll take this over to the other side as a minus 4.9, over to this side as a plus 4.9 meters per second. Times t squared is equal to 26.2 meters. And I can solve for the time. And I'll call this time t2 because this is the time that it takes to drop from here down. So t2 would be 20, well, this is going to be this divided by that, and taking the square root, I get a t2 of 2.312 seconds. And so the total time in the air is the sum of those two. Okay, it was this much going up, 2.245, plus this much going down, 2.312, and so that gives us a total time in the air for 0.557 seconds. And that's total time. Okay. Now I've done this, and there's different ways of doing it. In fact, on the solutions that I passed out, I did it a slightly different way. Notice in this one, here we started with the velocity, saying when is it going to be 0 up on top? I get the time for that. Then I can go into the y equation and stick in that time, and then I can get the height. So you can, however, say because this equation came from these two where we eliminated time. Again, in this one we solved for t, and then we ended up sticking it back in here, and we've got it. It's not a difficult operation. We've got it there. However, in my solutions, and I think I won't go into it here, but you can take a look at them. I use this equation, eliminating time, and going right for the maximum height, and I can do it with one equation. Then I go on to doing this equation, and I did this really 2 times. I used this classic y equation as a function of time and going back down, and I did it in 2 parts. I said I'm doing it going up, I got the time, and then the time going back down. However, you can use this equation. You can say that y is equal to y initial plus the initial velocity in the y times time, and we're going to have a minus 1/2 gt squared. And I can use this for the whole trip, going up as well as back down. This will be good. I can say when I'm going to end up at the very end, that's going to be 0, is going to be my initial position was 1.5. My initial velocity was that 22 times t minus 4.9 times t squared. And I can solve this one for the time in the air. So you will find that you will get the same answer. However, you could say, well, I'm doing that with one equation. Here I had to do it in 2 parts and put it together. Lots of ways of doing this. This is kind of shorter in a sense that the math seems simpler. However, I also get stuck with the quadratic, which for most people with your calculators, no problem. No quadratic, stick in the constants and out pops the answer. You don't have to show him the quadratic equation. He assumes you can do the math, and you can use your calculators to do that. So there can be multiple ways of doing problems. Whatever you're kind of comfortable with. Kind of this first thing I went through is kind of taking you through a process, is kind of thinking through that whole process to get an answer. But your math can be very powerful and just take you on the whole trip in one shot. So hopefully you can pick up on that. Okay. Yeah. Oh, excuse me, just one second. You have the battery signal on. Okay.
I moved it.
Oh, yeah. Okay, is it on there now?
No.
Oh, it's okay.
Oh,
It's gone.
what happened?
Yeah, as long as there's power going in there, you won't see that battery signal. Okay. Yeah. All right. Hi. Okay. Yeah. Okay. Sorry for the interruption. We've got again. There's a few people coming in. If you want to pick up some practice problems, you can do that. Okay. Okay. Let me see what's. Oh, as far as one-dimensional problems here, let's get something a little more meaty. I'm thinking the extra problems number 1. Okay, I hope. Number 1, we've got Mark running at a constant speed of 5 meters per second, runs past Jim, who is at rest on a motorcycle. After waiting 3 seconds, Jim starts to accelerate at 1.5 meters per second squared to catch Mark. Okay, how much time does it take for Jim to catch and get in front of Mark by 15 meters? Okay, now we're going to use these kinematic equations. We've got really 2 people, Ken and Mark. Excuse me, Mark and Jim. And let me start off with kind of a picture. We've got Jim on his motorcycle here, sitting, let's say, stopped at the roadway. Maybe it's a traffic light or something. And let me kind of go up here. And we're going to have running by him is going to be Mark. Okay, so then Mark is going by. He is going to be going at a constant speed. Now I would suggest, will you do something like V initial for M for Mark? Okay, I need to distinguish between these two because I have 2 bodies and they each will have their own equations of motion. So Mark, V initial of Mark, and it's stated there this is at 5 meters per second, and he's at a constant speed. So what's his acceleration? Acceleration of Mark is equal to 0, so that's him. Then Jim is here. He's at rest, so V initial for Jim is equal to 0. And he is going to, when he does take off, he's going to accelerate at 1.5 meters per second squared. Okay, then the question is, of course, at first Mark takes off and gets ahead of him. He's going to wait 3 seconds and then take off and get him. So what we want to do is think of your separate bodies. You've got Mark and you've got Jim. Mark is, let me use our standard kinematic equations to take a look at this. I'm going to use this for Mark. It's going to be a 1/2, let me write the generic expression first, AT squared plus the initial velocity of Mark times time plus any initial position of Mark. And I would suggest that, well, right at the start of the race, let's just call that x equal to 0. So then his initial position is 0. That's good. He's got his initial velocity. That's going to be that 5 meters per second times the time. And let's even be cautious. Let me say the time of Mark here. And the idea will be this, that you've got two runners, two separate equations. So imagine you've got like two stopwatches in your hand. When Mark goes by, you hit his stopwatch. Well, this guy hasn't started to move. It'll be 3 seconds before he starts to move. When he moves, that's when he's traveling that way. And so we want to consider we maybe need to start his clock here. So a lot of ways of doing this, but I'm just going to call that the time of Mark. And his acceleration is 0. So 0, this was 0, and so maybe I'll just write this as, this is going to be the x of Mark. And I should have put that over here. Okay. So I've got this equation for him. I can't do too much because I don't know the time and his position, but that's the equation describing it. The x of Jim is going to be 1/2 the acceleration. This is the acceleration of Jim times the time squared of Jim plus the initial velocity times time of Jim plus the initial position, x of Jim. We're going to just make this starting line 0, so that goes away. That becomes simple. We're going to have his acceleration will be 1.5, 1/2 of 1.5 time of Jim squared, plus his initial speed. Well, he's at rest initially, so those two terms are 0. And so that is the x of Jim. Okay, now... okay, so the idea is that these two runners, two bodies that are in motion, are going to, very often in these problems we say, when is x of Mark equal to x of Jim? This is a little bit different twist. How much time does it take for Jim to catch and get in front of Mark by 15 meters? So I'm thinking this would be stating this would be x of Jim minus is equal to the x of Mark plus 15 meters. Does that look right to you? Okay, so we want to get, Jim is going to be not only catch up to Mark, but he's going to be in front of him, ahead of him by 15 meters. So I can go ahead and put this in here. This is going to be 1/2 of 1.5 times the time of Jim squared is equal to Mark 5 meters per second times the time of Mark plus 15 meters. Okay, now the only thing is we need to solve for a time, and I'll have to say that I find his statement is a little confusing. See if you agree. He says, okay, Mark goes by, and so that would be t equals to 0 for Mark since he's just starting off there. We don't want to start with t equal to 0 for Jim yet because he hasn't taken off. And until he does, we want to not hit his stopwatch. So again, Mark goes by, we hit his, that's the time of Mark. Then he takes off and goes. Now, he says, after waiting 3 seconds, he starts to catch him. How much time does it take for Jim to catch and get in front of Mark by 15 meters? Okay, now, what is he talking about? How much time? Are we talking about Jim's time, or are we talking about Mark's time? Jim's time?
Isn't Jim's time 3 seconds after Mark's?
Mm-hmm. So how much time did Jim take to catch up?
Okay, so that's as he goes by, and I think that's...
So they're including the Mark's time.
Yeah, part of the time he's resting. I'd actually would be up there asking him some questions on this. Now, he did give some hints, and sort of the idea is hint, t and t minus 3 will be useful. So that's giving me actually a clue to his thinking, although I'd want to say this. I think what he wants is, he wants the time that, the Mark starts going by. So that's when the clock starts. And then when he finally catches up and gets in front of him, that's what he wants. So I think he actually wants Mark's time. So if we're going to relate these things, the time of Jim is equal to the time of Mark plus or minus 3 seconds. Okay, that's the question. Okay, so the idea that Mark's time goes by, now you could think this way: when t equals to 0 for Jim, Mark is already 3 seconds ahead. So that is really, that's when he starts. That's when t Jim is 0. So I think minus 3 seconds will do. Does that make sense? It's easy to get confused on this, kind of dyslexic with it. My trouble. I can take that, and so I believe we want to put that in for Jim's time, and we want to solve for Mark's time. I think that's what he wants to know. He wants to know the time on Mark's clock is ultimately what he wants to know. So I'll put that in. I'll put in this time of Mark minus 3 squared is equal to 5, time of Mark plus 15. It's looking like, wow, we got a quadratic, and you can do the math, but we come up with a time of, what do I come up with here? I get a time of 13.48 seconds, and so that's the time. Now they do also, because it's a quadratic, we also get another time. We get a time is equal to minus 0.81 seconds. Ooh, so what's that? Is that physically real? Yeah, the idea that the math doesn't really know that this guy is just sitting here waiting to take off and accelerate at this. As far as the math is concerned, it's good for positive values as well as negative values, and we get a negative value of time. It would have happened in reverse had he already been in motion. So this is, we want to scratch that one, and this is the physically real one. Yeah, David.
You have the one that Mark is at 15 meters out. Why not have that be when the time starts? 0 for both of them.
Oh, and run it backwards.
Just run it forward from
Okay, this is actually when they connect. I think there can be a lot of ways of doing the math, but we want to get the time from when he passes him till when he not only catches up, but gets ahead of him by 15. So, yeah, I think it's best to, I mean, we could kind of run the clock backwards, but I think it's better to just keep the clock going forward doing that. So hopefully you can follow that a bit, and you can also see that this thing with times can be a little confusing. And again, I don't think from the statement of that, I'm not really clear on which time he was actually asking for. Anyway, you can think about it and interpret the way you would like to. Okay, let's do some, how are we doing on time? Okay, we're in pretty good shape here. Let's do some projectiles and get into kind of chapter 4. So chapter 2 was this kind of one-dimensional motion. These are a couple of examples of that you might have to face something like this. The idea of projectiles, I'm going to use one of these little things here, little projection. So we fire this. If I fire a projectile, let's say I shoot something off to the side, and in the x direction, there's no forces in the x. You've gotten a little bit into that, and therefore there's nothing going to slow it down in the x direction other than like air resistance, and we'll get into air resistance later. Right now we're just dealing with idealization. There's no air resistance here, so anything that is fired out, it would normally, if there was no gravity, would be going at a constant speed, and these kind of stroboscopic images are going at a constant rate, and that would just indicate it would be moving at a constant speed. However, in the y direction, if I have something like a ball and I just drop it, it's going to accelerate, and these space intervals are going to get bigger as it falls. It accelerates like this. So what happens if I fire a real projectile? I shoot it in the horizontal direction, but because of gravity, it falls in this distinctive parabolic arc. The idea for this, and this is the potent idea in all of this stuff with projectiles, is that the motion in the x direction is independent of the motion in the y direction. Or I should say, they're time dependent. At some time t, when it would be like here, it is also fallen this. So it's really got both sense of motion, both in the x and the y. They're together, and they're always locked together in time. At some time t, it has moved along the x direction at a constant velocity, and it has fallen with a constant acceleration, and these two are locked on to one another. And so in doing problems, we can usually we'll go one or the other. If I want to solve this, the thing that's tying them together is some time t. When they are at this position, they are at the same time. So let me take that idea and let's go back to that number 3 of your practice problems. We had that race car driver drive off the cliff, and I kind of left the problem hanging on the cliff there. And let's take a look at that. So this is number 3 continued. Again, we had this, remember, it was a 20-meter high cliff. We went off the cliff as a projectile. How fast was that? I wrote that down and I've lost it here. I've got it here. Okay, I got a velocity, or we got one before, the velocity going off in a horizontal direction. Its velocity, we could say, in the x direction, since it's just going that way. And that was 11.34 meters per second. Now, it's going to go on a parabolic path and crash down on the beach below. And we want to know how far from the cliff did this land. I'll just call that x equal, let's call it equal to x. Okay. Now, the idea that this motion can be thought of this way with a falling body, and just start with something that is going to, let's say up at the very top, you're just holding this, you let it go, it accelerates, comes down. And being that tied into the motion at every point is going to go in the x direction. So first off, we'll say in the y direction, and we will have, I want to get the time that it's in the air is really what I want. The time that it falls, going from here to here. And I'll use instead of x, I'll use y is equal to y initial plus the initial velocity in the y times time plus the 1/2 at squared. So let's start with that. The y is going to go, let's see, it depends where you want to call y equal to 0. We could either do it up here or down here. Maybe I'll just do it down here. That's sort of the ground down here. So this is y is equal to 0. So my initial height here on this thing is going to be 20 meters. Oop, 20. The y in the final should be down to the ground, should be to 0. The initial velocity in the y is 0. So there's nothing there, but there will be an acceleration in the negative direction. That's going to be a minus 4.9, 1/2 g times t squared. And so we can solve for that time that it's in the air. I'll take this over to the other side. 4.9 t squared is equal to 20. We can then 20 divided by 4.9 square root, and we can get the time that it was in the air. And I get 2.02 seconds that it's in the air. Now during that time, it's going with a constant speed in the x direction. So in the x direction, we get x is equal to x initial plus the initial velocity in the x times time plus 1/2 a t squared. The x is what I want to find. I'll make the initial x right at the base of this hill, x equal to 0, so that makes that term 0. The initial velocity in the x, we've got that. That's 11.34 times time minus 4.9 times t squared. And then x would be that distance.
Why did you put gravity in the x? Yeah.
Oh. So you could, once again, I could make myself a fool. Okay, yeah, what about acceleration in the x? Okay, I make these mistakes for a reason. I'm lying, but okay, yeah, that's 0. Yeah, we don't have gravity in the x direction. We just have that. Yeah. So there's method in my stupidity here. So I'll go ahead and put that in, and we can solve for x. And I got, maybe I'll just write down what I've got here. 22.9 meters. Okay, you got that too? Good. That's reassuring. Okay, good point. Yeah, what is the acceleration in the x direction? 0. Yeah, it goes at a constant speed in the x direction. Boom. And that's what these evenly spaced things represent. And the idea, if I get the time going down to here, and then I take that same time for the thing going at a constant speed, I should get over to here. And that's where I'd be landing. Yeah.
Did you show where you got Vx from?
Oh, x. I did that earlier. You maybe came in after the start. Right at the beginning, I went through this first part. The solution's on the handout there. Okay. Yeah, I dropped it there. I wanted to talk about non-constant acceleration for this part, and then I wanted to postpone discussing. Yeah, that's all right. I'm sure there's other people confused. Okay, let's, I think we're ready to get into something. Oh, no, let's do a couple simple questions, and then we'll get into something more profound or tougher. Okay, now this idea that we have here also works for projectiles that are shot up. The idea that shooting something up, if you just went and shot it straight up, falls back, going along the ground at a constant speed, those two motions get tied together. And again, the thing that ties them together is time. At the time that this is here, the time, whoa, you see, oh, I guess I don't have, oh, I got them down here. Yeah, the time that this is here is the time that this is here. We always want to tie between back and forth. We did the idea, I've got the time from the y motion and take it into the x motion. Let's do, it's a pretty good example. Let's do one more simple one here. Okay, how about this one with the fire hose? Number 5. We've got.
The extra problems?
No, actually, this, on the practice problems. I'm pausing because I'm wondering if I shouldn't just jump to the. Well, let's outline it real quick here. We've got a firefighter. We've got a building. This is just number 5. So a firefighter 50 meters from a burning building. So he's 50 meters. He's going to be firing some water at 35 degrees above the ground. Yeah, actually, we probably should do something like this. And he's got the water is coming at 45 meters per second. shooting out of this thing. So I expect this thing is going to take off and be some kind of a parabola, and it's going to hit the building. And they want to know at what height that it's going to hit the building. And yeah, that's all he's really asking for. What height does it hit? Oh, the firefighter is standing out here 1 meter above the ground, so that's where he's shooting that thing. And we want to find the height that it's going to hit. Now, we haven't talked much about vectors. The idea that we want to break this velocity, which is 45 meters per second, we want to break it up into x and y components. There's going to be a component in the x direction. Let me just call this v naught for now, for kind of the initial velocity. And we want to imagine putting like a little rectangular box around this thing. This is going to be v initial in the x, and there's going to be a v initial in the y. It's kind of small. I hope you can see that. And in terms of the trigonometry here, we've got a 35 degrees angle here. I should be able to get the velocity in the x direction, initial, is going to be this initial velocity times the cosine of 35 degrees. Okay, that's just this side adjacent to that angle. V initial in the y should be equal to V naught times the sine of 35 degrees. Okay, so this is how we need to break this down. And then what we're going to do is similar to this last problem. We're going to take an idea that we'll deal with the x motion and the y motion and deal with them rather independently. In the x motion, we can get some information from this. We can say, well, how long does it take to get down here? Typically, we're always solving for time. And I'll use this x is equal to the initial x plus the initial velocity in the x. I call that v naught in the x times time, plus the acceleration, which I admonished is 0. Times t squared, we've got that. And so I've just got my basics here. Usually for projectiles, it might be convenient just to make that x equal to 0. So that's 0, and of course the acceleration 0. And then we just have a real simple expression. We get x is equal to the initial velocity in the x, but be careful, when it's going up that way at this angle, we've got to include that angle. That's going to be v naught times the cosine of 35 degrees. Times time. And now they tell us what the x is. That is, we want to get the x of the burning building, where that's going to be. That's 50 meters away. V naught is 45 meters per second times the cosine of 35 degrees times time. And we can certainly solve for the time. That's easy enough. We'll get that, and I get a time of 1.36 seconds. And I can take that, and what I want to do is I want to take that into the y motion. Because that's happening simultaneously. I'm getting the two of these together, and I can solve for where it's going to land. I'll use the y equation. That's going to be y is equal to y initial plus the initial velocity in the y times time plus 1/2 the acceleration in the y, which is going to be a negative 1/2 gt squared. Right? Okay. And for g, I put in 9.8, not a negative 9.8. I've already got my negative sign here. So when you're using g, always use the absolute value, and then put your signs in here is the clearest way to avoid problems. So I've got my time. I got my initial y. Well, okay, the firefighter was 1 meter up. So that's 1 meter. Plus the initial velocity in the y. Here's where I've got to watch myself. I've got my initial velocity times the sine of 35 degrees. minus 4.9 times t squared. Oh, there should have been a t in there. Okay. And so I'm going to take that time, I'm going to plug it in, and this y will be the h, the height on the building that it's going to land. I know my velocities. I think you can kind of see where I'm going with this. This is 45 meters per second. From this, I should be able to plug in those times, 1.36 seconds into here, back into here. Now you just crunch the numbers, and I get a height of 27 centimeters. I'm pausing, yeah. Centimeters, 27 meters. Yeah, okay. Notice the y, I made my y equal to 0 here. The book often will, for projectiles, they always put their coordinate system, almost always, put it right here at the takeoff point. So then the idea is you would solve for y out here. You would get the value, it's going to up above the 1 meter mark, and to get the total height you need to add in a meter. A lot of ways of doing that. I kind of built that into the problem, and I think you should be comfortable with that no matter which way you do that. Okay, let's see, what other one did I? Okay. Actually, I think that will be good. I was going to do another one, but I think you got my solutions. It can be okay. Let's while I'm doing this, we've got a little bit of time. Something they use quite a bit in some of the homework problems, and I get people not sure what's going on with this. They'll use the range equation, and the idea of that is if you're going to fire, yeah, let me hold on to this one for a second. If we've got, let's say, level ground, and you're going to fire a projectile from the ground with some v initial, and we're going to fire it at some angle. Of course, it's going to take off, and it's going to go on a parabolic path. And we're going to deal with this strictly on the level ground. We're going to call this distance the range of the projectile. And what we're going to want to do is do what we've been doing here. Let's do it a little more just symbolically to get the idea of this. We're going to want to break this up into components in terms of the velocity. We're going to have a velocity initial in the y and an initial velocity in the x. And from this, it's a little easier to start with the y motion first.
Is this
Oh, this is not actually on these problems. This is a more general equation. So I'm going to just back off a little bit and do hopefully a quick derivation of this. And again, a lot of times in problems, people, the homework solutions will use this, and students aren't always sure where it comes from. So with this y motion, I'm going to write that. Let me write the generic one is equal to y initial plus the initial velocity in the y times time plus 1/2 a in the y t squared. What I want to do is get the time that it's in the air. So it's going to start here at 0, and I want it to go all the way over here and end at 0. So I want this to be 0 is equal to the initial position, which was 0, from when it takes off to when it's back on the ground, plus the initial velocity in the y, which should be the initial velocity times the sine of theta times the time. And then we're going to have plus 1/2, or let me go minus minus g over 2 I'm tempted to put in the numbers here, and a t squared. Okay, so that's equal to 0. These are zeros. We can divide through by 0 as long as t isn't 0, and t equals 0 is actually one of the solutions. That's when we're back here. I want to get the time out here so it's not 0. And so I could go ahead and cancel with this and then solve for this, taking this over to the other side. G over 2 times t is equal to the initial velocity times the sine of theta. And solving for t is going to be equal to 2 over g v naught sine theta. Okay? So that's the time that it's in the air. While it's in the air, it's moving at a constant speed in the x direction. So if I take a look at x motion, that's going to be x is equal to the initial x plus the initial velocity in the x times time plus 1/2 at squared. And so I don't mess myself up again, that acceleration is 0. I'm going to make x equal to 0 right where the thing took off, so that's 0. The x then would be what I'm going to be calling the range of my projectile, that's r. And that's going to be equal to your initial velocity in the x, which is going to be the initial velocity times the cosine of theta, all times the time. And the time would be 2g v naught times the sine of theta. Okay, it looks a little messy at first, but let me, I'm multiplying this, so this is v initial squared. I'm going to have a 2 here, I've got a g, I've got a sine theta times a cosine theta. Okay, so that's the range. This 2 times the sine theta, does anybody recognize that one? It's probably one of your favorite trig identities.
Sine squared theta.
Yeah.
Oh, sine.
Yeah, so that's times the sine, no, not sine squared, or 2 theta, right? Okay, so that's the range going down range. There's some interesting things that take place with that. If we projectile range, boom, okay. Fire a cannonball. Actually, we're sending them all with the same velocity. Depending on the angle we launch them, one thing that you can see is at 45 degrees, if I put in sine 45 here, times 2 is 90 degrees, that makes sine as big as it can be. Let's see, question?
Yeah, like if you do plug in G negative 9.8,
Oh,
then you can actually really mess yourself up. Because
that's right.
when you have sine theta, cosine theta, it's hard to solve for theta.
Right. And I tried to allude to this. I didn't do a good job, and thank you for bringing it up again. Yeah, when I put in G, it's very often, it's very nice to deal with the symbols. G represents, when we write it, 9.8. Don't stick in a negative in that. I've already included this negative here, indicating I know it's down. So if I go ahead and stick in a negative 9.8 times a negative, it's a plus 9.8, and everything falls up and screws you up. So good point. Again, if you see the G, don't automatically stick it in as negative. We can very often choose our direction. Often we'll choose, you'll see in the next section, we'll start choosing down as positive. So then G is a positive quantity. So assign your directions based on that. And then again, this is 9.8 absolute value. Okay? Yeah, thanks. Okay, now as far as the maximum range on a projectile, if you shoot it at 45 degrees, it'll go the farthest. 45 degrees times 2 is 90. That makes this as big as it's going to get. Sine of 90 is 1, so that your maximum range is V initial squared over G. This is handy in that one problem where you throw the ball at 45 degrees maximum range, and then you throw one on the bounce. Well, you've got to color some range, forming simple ranges in there, and you can play with this equation there. It's a lot easier than going back to starting to play with all of this stuff. So you'll see that used in some of the problems. Now, it turns out that you also get two solutions. So you get a solution, let's say, think of the unit circle, and let's say you get a solution here. You do the arcs, let's say you want to get the angle for some range, you'll do the arc sign. And you've got some angle, let's say that angle is, let me just call it 2 theta now. There will be another angle, let's say 2 theta prime. There's going to be a sine of that, which is on the unit circle is this much. And you know that there's going to be another one back on the other side that has the same sine value. That's going to be an angle here. Let me call that theta. Let's say theta prime is going to be equal to pi minus 2 theta. Okay, so our two answers are either, let's see if I'm going to run into trouble here. Two answers, theta, or how to write this? Okay, we have two answers. We have 2 theta. We also have 2 theta pi minus 2 theta. That's going to give you another angle that, well, the sum of those have to be pi. So theta, or 2 theta, plus 2 theta prime has to be, in other words, this angle is the same as this angle over here. They have to equal pi. And so if theta prime is equal to pi, I'm getting myself all tied up here, 2 theta. Okay, let's see, I was going to look for a rigorous argument, and now I'm confusing myself. Essentially, you're going to have 2 answers, and divide this by 2. Let me just kind of give you the upshot of this so I don't waste any more of our time. The idea that any 2 of these things, they have to be 2 of them, so this is pi divided by 2 difference is the sum of these 2. So when you add like 15 plus the other one that hits the same point, it's got the same range, it's the other angle, always 2 angles, 75 and 15, they're going to add up to 90 degrees. Similarly, if you fire one at 60 degrees, it ends up over here. You're going to get the same range if you shoot it at 30 degrees, and that's where they hit. Again, the sum of these 2 end up being 90 degrees, or pi over 2. So that's, again, 90 degrees. Your longest one is just one of them, 45 degrees, or you could say it's 2 solutions overlapping, and they add together to be 90. So this is kind of an interesting relationship, and I apologize, I kind of trying to do an added insight into where these numbers are coming from, and I'm just confusing myself. So, okay, so this is the idea of the range of a projectile. It's only good on level ground, so it is a kind of a special case. Your very last homework problem is, well, let me allude to it in a little bit, but is a more difficult problem in that it's getting the range down a ski slope. But anybody get that one? So,
Which problem?
the very last one of your homework for.
I did it, but I got. I'm not sure what went wrong because I got that. I got instead of omega over 2, I just got omega. I'm not sure.
Okay, it's a tough problem. You need a number of trig substitutions, so I'm not going to do it here. If you want to see it another time, but it won't be on the exam for sure. But something that's closely akin to that has been on the exam, and as I erase the board, you can look at it. Let's get into something a little hairier. Number 7 on these practice problems, the ski jumper leaving the ski slope. 7. Let's see. We're at 2:30. I can do this. Would you like to take a break now, or should I? You want to go at till after this problem? Usually, I try to do the break in about in the middle. Usually, we go a little longer on the first part. Would you like a break now, or? Now? Okay, let's do that. What you may want to do is give yourself some thought. We'll come back, try to be about 10 minutes. We'll come back. Take a look at this number 7. I'm going to start to put it up here. And it's a little more involved. It's a good problem that illustrates a lot. So, yeah. Actually,
I got a question for you. On the test, is he going to have these pictures drawn out for us?